I think I did it on my computer. So I think we're ready to go. Yeah, everyone should get a message. So you're all very welcome. Thanks everyone for braving the anger of your significant others by joining me on Valentine's night. It was an unfortunate clash of timing when I first booked it, and one of my work colleagues got great mirth in telling me, "Did you just book a workshop on Valentine's night?" But I spoke to my wife about it, and she was like, "Nah, don't bother changing it," which hopefully is a good sign. But I'm now, as I say it now, I'm just kind of realizing that could be a bad sign too. So anyway, that's kind of where we are. So yeah, I decided let's just plow on anyway. And worst case scenario, if it if we end up with a very small attendance, that's just the way it goes. So yeah, so thanks very much for joining us. This is kind of a workshop series as part of Dublin Data Science. We started putting everything online as a result of COVID. We are hoping to come out of kind of COVID soon and potentially start hosting like in-person events or possibly hybrid events. I'm not quite sure exactly how to deal with that yet. Ideally, what I would like to be able to do is potentially have a talk that was also recorded somehow and then put the recording up on YouTube or whatever. How feasible that is, unfortunately, I don't really know. And that's probably not something that's really going to be discoverable for a while. I think some of the venues we use, that might be a possibility. For others, not so much. However, I think what will definitely be the case is workshops will always be online. So they will always be recorded. They will always get put online. So, and, if you stay tuned for kind of more details on that. I'm not exactly sure when we're hoping to have our next talk. And I'm also not sure if that's going to be in person or online. But yeah, we'll have details on Meetup, and you can check out my LinkedIn feed and stuff like that. I keep it there. But anyway, this is a workshop series that we've kind of been running now for quite some time. We kind of, as opposed to talks, workshops are generally a bit more practical. They tend to go longer as well. They're kind of, they're about 2 hours long, as I think I've mentioned on Meetup. It's designed to be very interactive. I found sound can be messy though. So what I'm going to ask people is if they've got any questions to pop them in the chat. And if it's a question where I need more information, whatever, or people just aren't comfortable talking, I'm more than happy to do everything through chat. But maybe during the break, or if it's particularly, if it requires a bit of discussion, I'll ask you to unmute, and we can kind of continue on that way. Don't feel in any way bad about asking a question about anything I say. The more questions you ask, the better it is for me, because it's just not me staring at a screen for 2 hours and blathering on about statistics. So the more interactive we can make this, kind of the better it is for everyone, because it can be actually one thing they don't talk about, or maybe they do, but I certainly haven't seen any, is just it can actually be quite exhausting, like talking to a camera for 2 hours without a whole load of feedback. A lot of people have actually said, and I definitely agree, that it's actually a lot harder to talk to a screen in this way than it is to deliver like the equivalent content in person, presumably because in person you're just getting all that extra sensory information, like you can see what people are saying, sounds in the room, all that kind of stuff. Whereas when you're here kind of by yourself, your brain has to work harder to kind of fill in all that information. So this is a very, very long-winded way of me saying, please don't be shy about asking questions. I'm more than happy to go down like minor tangents, or repeat what I've explained, go through some stuff. If I make some kind of general statement and you would like a more specific example of what I'm talking about, please don't be shy in asking me. I'm more than happy to do that. Yeah, and so basically that's kind of the way I tend to roll. All of the materials for this is available on GitHub. Actually, let me just bring that up right now. For those of you who are interested, I do have a GitHub repo. Pretty much everything I do that's related to pretty much there's a bunch of different things in there, but I put everything into this data workshops. Now, as you can see, each folder is basically a different workshop or whatever. It's this WSCLV base. So pretty much everything, and I actually just merged it all onto master a little while ago. So it should be reasonably up to date for all the stuff that we're doing today. And yeah, you can get that if you want to like download it yourself. It should pretty much run as is. There's a bunch of data generation that needs to run. I also have set it up that it runs in a Docker file, and I've got a make file with a bunch of targets that kind of deal with all that stuff. But yeah, so, but like I said, everything is rendered here. I do have a little version running. Oh, it's actually still something. I'm just rebuilding everything in the background. So if we do need to give examples or whatever, I can actually. I'm one of those people who I try not to do it too much, but I'm not entirely what you would say intimidated by coding live. So if I need to show something by just bringing up the code, I've got the console there, so I'm happy to do that. All right, so you're all very welcome. Like I said, it's for the February episode. Oh, I see a bunch of people have came in. Yeah, it's weird. I disabled the sound when the chime when people leave and enter. So it's definitely less distracting to have. So anyway, yeah, it's great to see a bunch of people. All right. So in this series of workshops, like I said, we're dealing with Bayesian statistics, Bayesian data analysis, and specifically through the implementation of a customer lifetime value model. Now, again, I'm very conscious there's a bunch of people who weren't here before, and even though you were, people may have been here, because I do recognize a bunch of names in the people who have arrived. What I've been teaching kind of Bayesian statistics for a while. It's kind of my preferred method of doing data modeling and building models and all that for various reasons, some of which we'll probably end up addressing as the workshop series progresses. But one of the issues I've always had with it is that the applications of it have always been a little bit contrived and have always been kind of, yeah, so what? They've just been a bit meh. And that part of that reason was for me, I was trying to come up with very simple examples to try and so that the details of the analysis didn't obscure the actual underlying stuff I'm trying to teach. But also, in some ways, it means that you have some idea of what it's like, but you don't really know what to do with it afterwards. And I've been very conscious of that for a while, specifically with the examples. So what I decided to do last year when I did my workshops, Soup to Nuts, which, like I said, you can get on YouTube, one of the original motivations for actually doing that was to build these kind of models, because someone had told me about it, and I hadn't had any experience with transactional level data, like on retail. I knew there was some data sets out there, but I didn't have a lot of experience with it. So I kind of created the workshop thinking those would be the models I built. Now, as it turned out, what we're kind of doing here, and for reasons that we're going to go into throughout this workshop, the model was a bit too sophisticated for what I was trying to do last year. So I decided this year I was going to do kind of customer lifetime value, and I realized actually it's not too complicated to kind of teach Bayes and this at the same time. So I'm kind of trying to do the two things at the same time, providing motivation for one and showing you how you can kind of combine both. And what I'm hoping to convey from that is to show that using Bayesian statistics with an actual real world example will hopefully give people an idea of how these things work and in practice, and give, I don't want to say it's very practical, because we're probably, by necessity of time and whatever, there may be a few things we're going to have to gloss over, just for the nature of the because again, the scope, just trying to keep the scope as on target as possible. But yeah, so what we're essentially going to build is using Bayesian stats, introducing all that kind of stuff, and building customer lifetime, specifically what a subset of customer lifetime value models called buy till you die models, which were developed by a guy called, I think, Peter Fader, is the one who kind of was particularly popularized it, even though it's been around for a while. And using statistical inference to build and fit these models, and then show how we can kind of use them in practice. So in the last workshop, kind of I introduced the whole thing. I kind of introduced some basic concepts of probability and conditional probability, how Bayes rules works. We talked about how it works with integrals, all that kind of stuff. And we kind of went on, and we discussed a bunch of things, and then I kind of moved on to talk about this. One of the things to discuss, though, that often gets overlooked, and like one question that people asked is, well, why was Bayesian statistics not more popular if when people cite its benefits? why did essentially frequentist methods become more popular, and why was Bayes so totally unknown until very recently? And I mean, there's a couple of reasons for it, some of which are political, but I think the key thing is it was very, very difficult until recently to actually do this kind of stuff in anger. And the reason for it is basically this. Let me just zoom in. I presume everyone can see that. Is that, I'm going to put it up to 150. Is that big enough? Maybe I'll go a bit more. I'll go maybe 170. Just put in the chat, is that kind of big enough for everyone to see? And particularly I want to highlight kind of this formula here, which is the continuous case, which is in most cases we're dealing with continuous values. So the continuous case is much more interesting than discrete variables, for a number of different reasons, which I won't go into. Generally, you want to be dealing with continuous valued inferences. So, but ultimately, what it boils down to is this is an integral, and theta. So, just to put it in, d is the data you've observed, and you want to do inference on theta, which is the parameters of whatever model it is that you're building. So you have a bunch of models. You have that model is parameterized by a bunch of values that we're denoting theta. Essentially, any statistical model, realistically speaking, is basically trying to say, what does that data tell us about the parameters theta? And from some jiggery pokery Bayes rule, it essentially boils down to this. So we call this the posterior distribution for theta, which are the parameters in our model. So to give an example, what exactly do I mean by that? In a regression model, for example, every parameter in our regression is a vector in theta, right? So you'll have one value for every continuous variable, and then if it's categorical, each one will, it's k-1 values and so on. So therein lies the problem for a lot of this stuff, is that even relatively simple statistical models, you will end up with 10, 15, 20 dimensions in your model, right? If you have a regression model, let's say, and you're fitting, a curve of, let's say it's a really simple, you're just fitting some kind of curve, right, with a third order or a cubic spline type thing, you'll have at least 4 parameters. You have your intercept, your x squared, and your x cubed, right? So that's 4 parameters, and that's a really simple one. Like in most regression models, it's very easy to build a regression model that will have 30, 40, 50, 100 parameters in it. Very simply, like every categorical is k-1, that kind of thing. The problem with doing integrals over that is you just kind of run into the curse of dimensionality. So as your parameter space gets bigger and bigger and bigger, it becomes more and more computationally complex to actually evaluate those integrals. And we need to evaluate those integrals to calculate our posterior distribution. That's kind of unavoidable. And we need the full probability distribution. So unlike, say, maximum likelihood estimates, where we're finding a single parameter, so we're getting like a single point in phase space, in Bayesian statistics, the output is a distribution for those parameters, right? And that's what we call our posterior distribution for theta. So doing that has been very, very difficult in the past. And the only real way to do it is to create essentially sample from the posterior distribution. And we end up with a representative sample. So you end up with, say, 2,000 iterations from our sample. And that is a sample from the posterior distribution. And that gives us all the different values, as a vector. So that vector has 2,000 samples in it. And that way we can kind of capture all the different intricacies of the different parameters together. And that gives us, so whereas in maximum likelihood space, we will just have one value for that parameter. In Bayesian statistics, we have 2,000 possible values. And, that gives us a sense of our uncertainty that's captured both on the model side and the sample side and all that kind of stuff. Okay. And that it just becomes very complicated. Now, we have technologies now in the last kind of 10, 15 years. We have, we've figured out ways to do this. Computers have gotten a lot faster, memory, processing power, storage space, all that kind of stuff. It's gotten much, much more powerful. So now these kinds of problems have came into the realms of feasibility. And to be honest, some of these are doable with a modern day laptop, with a relatively modest, say, 16 gigs of RAM. You could probably solve some of these problems pretty quickly. I'm just going to take a quick sip. So that's kind of where we kind of got introduced all this. Now, How we do these today is we use a programming language called Stan. And Stan is something I'm going to get into a little bit later on in this workshop. I'm not going to introduce it straight away, simply because to start off, we don't necessarily need to, because we can start without, a couple of different bits and pieces. But once we start talking about Stan, we need to get into the details to a certain extent of what it does. Now, I don't necessarily, I haven't really covered that in the materials for this workshop. Instead, I'm just going to point you at the Stan guys themselves, who have loads of really high quality stuff on this, but I will talk in very kind of high level terms what's going on and why it's important and how it falls over and all that kind of stuff. But yeah, so that's basically what we're going to cover today. We're going to start using basically these kind of Bayesian statistic methods to perform some inference on our data and then start to see how these things kind of work. I don't want to say in practice just yet, because what we're dealing with are still kind of toy models. We're probably still a workshop or two away from using real world data, maybe longer, depending on how things go. I'm not, as I said, I'm kind of doing this workshop as I go, so I can't say for anything, for certain. But we're kind of approaching how these things would work in the real world. Now, before I move on, does anyone have any questions? I notice actually, geez, we've quite a few people have joined in the last little while. Does anyone have any questions about anything I've said kind of before we start properly? By all means, please put them into the chat. I'm kind of happy to address any questions about anything I've just said while I kind of get started. So essentially what we're going to boil down to, and this is all we can really do. I mean, ultimately it's what happens is the output of a statistical model is this posterior distribution for the parameters. And then everything that we derive as a result of that is basically operations on that posterior distribution. That's basically what we're doing. Okay, so what we have is some, actually, let me just load this up because I can show this here. Where is the data exploration? There we go. So we have a whole bunch of retail data. Now, this is the real life data that we had kind of written before. Oh, so this comes from the real world data that I downloaded online. We aren't going to use this today. I've created some synthetic data that we're going to use for the next couple of workshops. But just to give you an idea, it's transactional data. So you basically have a customer ID. And actually that's even more detailed because that has every single basket. But what we're boiling it down to is essentially each transaction has basically a customer ID. We've got some cohort information based on the data, and we have a timestamp for when the data happened, and then how much money was spent. So it's relatively high level information at the moment, right? We're not really dealing with individual products or any of that stuff, mainly because for a couple of reasons, but the main one is that when the basic buy till you die models don't really focus on the details of the transactions themselves. What they tend to focus on is just how many transactions occur and for how long does a customer transact. And then an extension to the model also, how much do they spend when they do transact? But the details of those actual transactions, like the products they're buying and all that, that's kind of beyond the scope of a model, at least the initial models that we're going to be dealing with. Okay, so we're not going to, so all we really care about is who transacted, when did they transact, and how much did they spend. And to be honest, the monetary aspect of that, we're not going to worry about for a while. That's kind of going to come a bit later. And because we're dealing with real world data and there's a whole bunch of kind of issues, and to get started, I'm actually not using the real world data to get started. I have some data code. If any of you are interested, it's part of the worksheet. It's part of the repo within that directory. I've generated synthetic data. And the reason for that, it sounds a bit stupid, but the reason for that is by generating synthetic data, we kind of know what the answer is. So we can build models that should be able to recreate the answers that we used to start our data generating process. So we essentially generate data with like what we're calling a generative model, which is a model that basically generates the data. And then we take that data and we use that generative model to fit the data. that we get to recover the parameters. And what we should be able to do is the outputs of the posterior distribution should match the inputs that we've got. Now, that sounds kind of pointless. I appreciate it's like, of course, we should be able to recover the parameters, but sometimes they aren't. And essentially, the way I was kind of, Joe, someone was asking me about this the other day. What we want to see is our model reversible? So in other words, if we can see, if we like, is there an inverse model to what we're building? Because if we're not, then we're in trouble. Because if we can't even create synthetic data that then recovers those parameters, we have a problem in how we've actually built our model. Because when you go to the real world, you know that the model that we're using to fit the parameters on is only an approximation of how that data was generated in the real world. And if the model we're using to fit the data on can't even recover like the parameters from a data that was actually generated by the model, then we know there's a problem. We have to essentially fix what we're doing. We either have to change things or what. So it's actually a thing in STAN that they've introduced recently. They call it simulation-based calibration. But essentially, it's a way of diagnosing your models to make sure that you haven't made any mistakes, or that what you're trying to do is actually doable. Like, is this model, maybe this model is just dead on arrival and you shouldn't be trying to fit real world data to it because it can't even recover the parameters for synthetic data. So that's basically where we're starting, right? And we're going to start with very simple models, nothing particularly complex. And like I said, the two things we care about with customer lifetime value, particularly for buy till you die models, is there's the frequency component, and then there is the essentially the, I don't want to say recency because it's not quite right. There's how often does a customer transact, and then how long is a customer active on my system. So there's two things. So essentially there's a frequency component and there's what's called the lifetime component, right? And what most of these models do is they have different ways of modeling those two aspects of one another. Now, for the purposes of tonight, we are going to completely ignore lifetime. We're just going to assume that essentially a customer, you know, is born at the start of a year. We're going to do it over a period of a year, and that's why this data is very kind of abstract, like essentially synthetic and not particularly realistic. It starts at like beginning of the year. A customer starts, they transact throughout the year. They never churn or they never go off the system, whatever. They transact at whatever frequency they need to transact at, and then at the end of the year, you know, they stop transacting basically. So that's essentially the model that we're going to work on now. Like I said, it's an unrealistic model because in reality, we also have to worry about lifetime, and we also have to worry about the fact that customers start, you know, customers are constantly joining and leaving. So we also have to kind of manage that. But that's kind of for a later version. We're going to start with really, really simple things just to get a handle on how things work and see basically, does that actually work, and think about realistic stuff. So that's essentially what we're going to work on tonight. How we do for time? 7:30, perfect. Okay. Now, I'm very conscious, like I said, I've been talking forever. Does anyone have any questions about what I've talked about so far? I'll just give people a sec while I have a quick sip. By all means, ask away if you do. All right, so we have some very simple data, and it's always good to visualize what you've got. So that's basically what I've got. I'm going to do here. Let me just try and get that perfectly centered now. God damn it. Hold on. Yeah. There we go. Okay. So this is just a very simple visualization of the transactions that we've generated in our synthetic data set. Okay. And these are just a sample of customers. I filtered out a number of transactions. I can't remember exactly how many. It's probably up there in the code. But essentially, I've just created a horizontal line for each customer. And then whenever a transaction occurred, I've just put a dot in it. So you can see there's, you know, varying frequencies for our different customers. Like this customer here, and these customer IDs are just random strings just being generated randomly within R. These are all kind of the dots. So you can see this is a relatively high transactional frequency customer, whereas the one above it, this SQC, so SP4 is very high transaction frequency, SQC is relatively low transaction frequency. So the point we have is that we have a certain amount of what's called heterogeneity in the transactions of our customers. So some customers are going to transact a lot. Some customers aren't going to transact very frequently at all. But they all kind of have the same lifetime of 1 year. and they transact throughout the year. So with that in mind, what we're going to do is try and get from the data that we've observed, we're just going to try and perform some statistical inference on the transaction frequency of customers. Okay, that's basically what we're trying to build tonight. So the way to think of it is that when a customer is kind of born on the system, for want of a better term, as in born being dictated by when the customer first transacts. So the first transaction on the system, the customer is born, and then the customer is essentially assigned a lambda, which is the transaction rate. So how often does a customer transact? And we model that through a Poisson. Now, I know a couple of people the last time we talked needed me to explain the Poisson distribution. Does anyone need to do that? Now, don't be shy. I'm happy to talk about it. Essentially, we're dealing these as discrete events. So it's a counting model, essentially. So what we're trying to count is how often does someone transact on the system over the period of a year. Now, does anyone need me to quickly explain how the Poisson model works? I don't see anything in the chat, so I'm just going to assume that essentially. So the idea is the Poisson distribution is kind of the basic distribution people use for modeling count data when you're counting events. So it's a single parameter. It's not two parameters like a lot of probability distributions. It's just got one, and that is the transaction rate. So, for example, and the idea is it's over a given unit of observation, and that is usually time, but doesn't have to be. What is the average number of events that occurs per unit of observation? So to give an example, usually it's time. So over a period, let's say I wait, if my unit of time is say a week, in a week, how often does a customer transact? So if we would expect, a customer to transact every week, well, then the Poisson rate is 1. If we would expect them to transact 10 times a week, that would be a rate of 10. And if we do expect to see one event every 10 weeks, it will be 0.1. Okay. Now, that doesn't necessarily mean that a customer will not transact more often. In fact, depending on the probabilities, you will likely see more often, like it will change. That's just an average. So even though the realizations of a Poisson model are always discrete, it's integer numbers, 0, 1, 2, 3. The parameter lambda is continuous from 0 to infinity, right? And so it doesn't matter. It can take any value, and that just dictates. So the Poisson is a bit weird because while it's parameterized by a continuous variable, its realizations are discrete, and that sometimes can throw people a bit. It took me a while to get used to the idea. For example, like how does the central limit theorem work with it? The point is it still works. It just kind of does slightly, it works in a different way to the way you would expect it to do based on continuous distributions. So essentially what we have is, if you think of the data generating process as you have a cloud of customers over here, right? As here's when they appear on the system, they're assigned a lambda value. That lambda value does not change over time. That a customer gets one lambda value exactly. So there's a certain amount of model simplicity there already, because it's probably reasonable to say that it's not a homogeneous Poisson process. Like realistically speaking, a customer's lambda probably does change throughout the customer's lifetime, or at the very least, there's like a seasonal effect. So you might have a customer who transacts more often at Christmas, for example, or maybe in the summer, depending on what the industry is. If you think of it in terms of retail, like public retail, you probably have a higher frequency at Christmas, let's say, rather than say in June. But for the purposes of this, we're ignoring all that. We're just getting one lambda process that is going to essentially fully explain the customer's transactions. And we've generated the data on that basis. So there's no non-homogeneity in there. However, as I said, each customer gets their own lambda, and that will be a distribution of values. Okay. And we can talk about how we model that kind of hyper distribution a little bit later. But that's basically the idea. So what we're trying to do at the start is we just want to get some inference on our customer transactions. And that way we can, once you know that, if we have a reasonable amount of information or a reasonable amount of confidence in a customer's transaction rate, well, then we can, like, it gives us more information. So maybe we want very frequent customer transactions, but maybe really frequent customers are actually problematic because of the processing involved. And maybe you actually don't want them. There might be a sweet spot in the middle where a customer, kind of the Goldilocks zone, as they say, where you don't have a customer that doesn't, you know, transacts frequently enough to be a good customer, but not so frequency that the overhead is very significant. So, you know, you've got to worry about all those kind of things too. But to do any of that, we actually need to have, you know, we need to have some estimates for what those transaction frequencies are. And that's basically what we're going to do today. And we're going to look at a number of different models for how to do that. Now, I'm just doing some sampling there. The data, the synthetic data I've created, I think has 50,000 customers in it. But for the, you know, that's just a lot. And I've taken out some samples of the data set, and just to make sure that whenever we're taking 1,000 samples, it's always the same one. I'm just kind of taking them out. Okay. So I mentioned before earlier that until very recently, Bayesian statistics wasn't really possible, wasn't really feasible. And that was true, but some statistics, Bayes was used for some things. And it appeared in kind of various guises. And the main way it was implemented was through the use of what's called a conjugate prior. So as I mentioned before, you know, Bayes' rule essentially boils down to this integral here. This, you know, this, so that you have this p theta, which is the prior distribution for theta. And then you have this PD given theta, which is known as the likelihood model. So essentially what it is and I talked about this at a lot more length in the last workshop, so I'm not going to go into too much detail here. But essentially, we use the integration to combine our prior knowledge, which is encoded in the prior distribution for the parameters, with the likelihood model, which is basically how we explain for a given set of parameters, how, like, what is the likelihood of observing the data we observed. And it's the combination of the likelihood model and the prior model that gives us our posterior distribution. And essentially, if we have a certain prior distribution for our parameters, combined with a very functional, so a certain functional form for our prior, combined with a certain functional form for our likelihood, that essentially we massively simplify this integral process. And what happens is that the Bayesian update process, which is that integration, just boils down to updating the parameters of the distribution. So to get, I know, I realize that's kind of a bit of a mouthful, but essentially you have all these probability distributions that are known as conjugate priors of one another. And in some cases, it's motivated statistical research for like useful likelihood models for explaining the data. If we have a conjugate prior that has a nice functional form that integrates with that, then that's a nice and handy way of actually kind of gaining some cheap and dirty statistical inference that we can calculate really, really quickly without having to rely on all these high dimensional integrals. Okay, so that's basically what we're going to do. So does everyone follow what I'm saying there? I'm just going to take a quick sip. Okay, so if you've, and you know, there's a whole bunch of ones. So for example, for the binomial distribution, where we're dealing with probabilities, its conjugate prior is the beta. So the beta distribution and the binomial distribution combine to give another beta distribution, and you just update the parameters of the beta. Anyone that kind of knows, has done statistics will not be surprised to learn that the conjugate prior for the normal likelihood is a normal distribution. So you have a normal prior, you have a normal likelihood, you combine the two, you get a normal distribution. You know, no real shock there. But for the Poisson distribution, we have a nice thing, we have the gamma. So if we have a prior distribution on lambda, so basically we use a gamma distribution to set our prior values for a lambda value, and the count model is modeled by a Poisson. The gamma and the Poisson to combine to give us a gamma posterior. And it comes with a very, very nice updating thing. So if we have a lambda prior here, and it's R and alpha, which is R is called the shape parameter, and alpha is called the rate parameter, and we observe X events over a period of N, then we just add X to R and N to lambda, and that gives us to alpha, and that gives us our posterior distribution. Okay, so it's a really nice way of doing it. So just to take a step back and have a think about that, just to kind of get, you know, to kind of get some kind of intuitive understanding of what's going on. If you think of your gamma distribution, your two parameters, your R and your alpha. So the shape parameter is kind of like the count parameter. How many did we observe? And then the alpha, which is the rate parameter, is like how many observation, what window, how big was our observation window? And like I said, that's usually the most obvious use for that is time, but it could be some other unit of observation. So for example, if you were using it to count defects in a manufacturing process, your observation count might be the number of items that have passed on the assembly line, or it could be like a length of, if it's like some kind of paper production or materials, textiles or whatever, where the unit is, so it's not necessarily so much time as it is what is the unit of observation that we're counting the events on. So that's our rate parameter. So therefore we kind of look at R is our number and alpha is our, so if you think of it numerator and denominator, then that's kind of, it gives us a distribution for what the underlying rate is. And then we observe X events over a period of N. Well, then we just add the count to our prior count, and we add the time window or the window to our prior count. And then we get our new posterior prior. So it's a very nice kind of way of thinking about it. And it kind of gives you some good intuition for kind of what's going on. And we're going to do some examples here. So let me just plot here with the gamma distribution. So has anyone here, like the gamma is one of those weird distributions in that it was kind of known by statistics people a while ago, and no, it didn't really get used a lot, but a lot more people seem to talk about it these days. And I'm seeing like a lot more machine learning and all these kind of things are starting to use gamma distributions a lot more often. Why that is, I'm not exactly sure. I'm sure basically people have just realized it's quite useful. Yeah, it took me a while to get my head around it. And the other thing that's quite confusing about the gamma is that there's a number of different parameterizations for it. There's a couple of different ways you can parameterize the gamma. The way I've described here with the shape and the rate is probably the most common and the most useful, but you sometimes will also get what's called the shape parameter and a scale parameter. And if you ever see that, the scale is the inverse of the rate. So you just divide one by the other. And I think basically it's like a lot of things. A lot of these things were kind of developed theoretically independently of one another. So in certain cases, it made more sense to use the scale. In other cases, it made more sense to use the rate. And the reason why I'm saying that is because the scale has a scale parameter in statistics has some very specific properties that can be very useful. So from a theoretical point of view, it might be easier to manipulate the gamma that way. But from my kind of intuitive point of view of how a gamma works, I like the whole shape and rate. And that's the standard parameterization in Stan. Now it's not necessarily a great way to fit a gamma distribution, which is something we're going to talk about a little bit later, possibly not in this workshop. I'm not quite sure just yet. Oh, hold on one sec. Am I losing power here? Oh, no, I'm fine. Okay. All right, now I see the time is about 7:45. I usually take a break around 8 o'clock, plus or minus 10 or 15 minutes. So what I'm going to do is I'm going to go on for a little bit longer, just talking about the gamma distribution. I'm happy to answer any questions as well. And then we'll take about a 10-minute break, probably in about 5 minutes, maybe 10, depending on how things go. We'll take a break, like let people run to the toilet, grab a cup of tea, do whatever needs to be done. And also I'll use that as a window to answer any questions that people may have in the break. So I'm just going to go on now. I'll talk a little bit more about the gamma. We'll take a break and then we'll talk about, how we use it in the real world. And again, like I said, I'm keeping an eye. I have a second monitor here. So if you kind of see me look up this direction, it's because I'm just keeping an eye on that one. If you have any questions, please pop them into the chat. I'm more than happy to kind of divert what I'm talking about or re-explain or whatever. All right, so basically, like I said, we're talking about a frequency model. So the first thing we need to do is figure out what our unit of measurement is. What's our observation window? Like, what's our unit of observation? So our unit of observation, because it's a retail, I figured, I mean, it doesn't really matter because it's all going to scale, but just from it made more sense to me to think of things on a weekly basis. I mean, you could very easily go monthly as well, but weeks just seemed like the most natural kind of cycle of repeating cycle, ignoring seasons and whatever. So we're going to deal with weeks in terms of how often. So all our transaction rates are going to be in terms of a unit of a week. So if we see a transaction rate of 1, it means that customer on average transacts once per week, okay? Which was 4 times per month, for example, and then whatever, 52 times per year, okay? So that's kind of what we're thinking. And now we're going to essentially set our prior distribution using this gamma distribution. And how often do we want to, you know, how do we set our priors for this? Well, that's part of where domain knowledge comes in. But for the stuff I'm going to talk about, let's assume that customers on average transact on the website about once a month. So then essentially we're dealing with a point estimate of 0.25. Now, another argument could be made that it means that the more natural unit of observation then is actually a month, because there is, for various technical and kind of philosophical reasons, you usually want to choose a scale that has unit values. For the purposes of this, I haven't gone that route, but that might be something it's worth doing. So for example, try to choose your unit of, in this example, when you're trying to figure out like what unit of time are we going to look at, you would choose the unit of time where the average customer transaction is once per unit time. Now I've kind of immediately violated that by going on a weekly basis rather than a monthly basis. It doesn't really matter from this point of view, but for various reasons, it made more sense in my head to think in terms of weekly. But it would probably depend on the particular use case. I could definitely see an argument in some cases if you were thinking about transactions, it could be on a yearly basis, or it could be on a daily basis, or potentially an hourly basis if it was, you know, if it wasn't transactions in terms of customer usage. Or retail, if it was something else completely that were like counting events on a website, then maybe the unit of time would be a week, or sorry, an hour, or maybe a day, or maybe a second, you know, depending on how big a frequency it was. But we're choosing a week. So on average, we're looking at 0.25 is kind of our point estimate for the average transaction time for a customer. Now, that's not to say that every customer transacts about 0.25. It means that the average customer is 0.25, but you're going to have some that will be much more frequent than that, and you'll have others that are a lot less frequent than that. So we're kind of going to look at a couple of different probability distributions that all have this. So basically, when you look at it, the mean of the gamma distribution is R divided by alpha, and that makes sense given what we've said earlier. If you think of R as the count and alpha as the window, R divided by alpha makes sense as kind of being the average for that distribution. But that doesn't, you know, that has an infinite number of possibilities. All we fix there is the ratio. So depending on how, you know, how we change that, how does that look? So if we go to say, that looks like that is a mistake. I think that shouldn't be, if it's 0.5, it shouldn't be 0.8. I think that's a mistake. But if we look at the different probability distributions, they all have an average of 0.25, but you can see as the numbers are getting bigger and bigger, they're kind of closing in, and that should be 20 as well. Oh, there's a number of typos. I'll fix that in the break. 0.25, they all have the same average, but you can see as the numbers, as the overall ratio, the total numbers divided one by the other gets bigger, the density is kind of tightening around the average. So essentially, the higher those numbers get, the smaller the dispersion gets. So this is kind of like a precision value. The more, if you can think of it as a precision, which is like an inverse standard deviation. Now that's not technically correct. It's not technically that, but that's kind of a way to think about it. As these numbers get bigger and bigger, even though the mean is staying the same, the spread of values around the mean is changing. Okay, and it's getting narrower and narrower. So essentially, the other way to think of that is that it's a stronger and stronger prior. And that can be a bit confusing. It's like, well, why is 1 over 10 less strong than 10 over 100? Well, the kind of the way to think of it is that as you do more and more things, as you do take more and more observations, if that ratio gets, stays the same, you're getting more and more certain that that is the actual true ratio. Your range of values is getting narrower and narrower because you're taking, like, it's kind of like the law. You can think of it kind of like an application of the law of large numbers. As your sample size gets bigger and bigger and bigger, your spread of potential values is getting tighter and tighter and tighter. Okay, so basically a way to think about how to set your priors is, how wide a set of values do we want to include in this? Okay. All right. So I'm going to take a break there because that's a very natural place to stop. And I also want to check this mess here that I've made of this and potentially fix it. So what I'm going to do is I'm going to put myself on mute, where I'm going to give people a break. It's about 10 to 8. So we'll come back about 8 o'clock and we'll pick up again. But in the meantime, if anyone has any questions or anything like that, by all means, put them in the chat. And I'm happy to address any kind of tangential stuff as well that people might want me to explain again, or if there's something I mentioned and you didn't want to disrupt the flow, but there's something I mentioned at the start of this that you'd like me to discuss, by all means put it in the chat and we can talk about it. But other than that, I'm gonna take a break now for about 10 minutes, and then we'll come back and we'll talk about basically using these priors with observations, combining the two to get a posterior distribution, and how we can use that with our transactional data to start making inferences on customer transaction frequency. Okay. So I'm going to put myself on mute and I'll see you all back in about 10 minutes. Hi, I'm just to let you all know, I'm actually back at the desk now. So if any of you have any questions, yeah, please, by all means, just pop them into the chat. Or actually unmute at this point when we're while we're waiting to get started again. Did you have a question, Neil?
No, just thought I'd give you the option of avoiding dead air if you want.
No, okay.
Yes.
Yeah, by all means, ask any questions if you had them.
No.
I'm just noticing the battery's gone quite low on this, and I don't really know why. That's annoying. Yeah, maybe turn down the.
Well, batteries occasionally start acting up.
Mm.
So
I'm just going to cut down on the screen
brightness. Yeah.
Screen brightness. That might kind of preserve. Maybe I just need to get my proper charger. It usually does the job though. Do you want to have a minute? I might go grab it. All right, I'm back, and hopefully that'll keep the chart. Sorry, I have a question here. Why are you using the gamma distribution? I think you lost your explanation. Simply because it's the conjugate prior for the Poisson. So the standard way to model count data is to use a Poisson distribution, right? So you have an underlying transaction frequency. Usually lambda is the standard symbol that you use for the transaction frequency. And when you have a Poisson rate for modeling that, if you use a Poisson distribution, then the combination of a gamma prior on the lambda plus a Poisson likelihood gives you another gamma posterior. And the update rule is that one there. So let's say I have my prior distribution for lambda, which is R and alpha, and then based on that, and that's what we're going to talk about now in the next couple of minutes. By the posterior is just if I observe X events over a period of N, then we just add R to X, so that essentially the two count values add up, and then the two observation values add up. And essentially it's a way of shortcutting the entire integration, which we would need to do otherwise. So that's what the benefit of conjugacy is. It means that you have a very nice way of doing the integration. So rather than having to actually do the integration of the two functions, you instead can just say, okay, I've got my observed data. I basically can do some summary statistics on it and update the parameters of the prior with those summary statistics to get my new posterior distribution based on the data. So it's a combination of the prior and the likelihood model together. And there's a whole set, you can actually look them up. If you look up online, there is a whole suite of conjugate pairs of likelihoods and priors that, along with like the updating procedure for it, if that makes sense. The other because of that fact, the gamma distribution is a nice kind of simple way of thinking about this, because it's a good way of, it's a very natural way to think about how to set your priors. You know, we can, because it's R over alpha is our mean, which is what we care about, and then we basically vary how big those numbers, you know, if you can think of it as a mean times a precision, the bigger the precision, the tighter around the mean that distribution gets. And we're actually going, and just to illustrate it there, oh sorry, it's the wrong one. So you can see here, like the red is, you know, weirdly enough, that all these have the exact same mean value of 0.25. It's just kind of, because it's a density function, it looks a bit weird. But as the numbers get bigger and bigger, this is actually 4 over 40, not 5 over 25, because that's just a typo. What's happening is, as it gets tighter and tighter, you know, we're basically more and more confident that the true mean value is 0.25. Okay, thanks for the question, though. Please keep the questions coming. I appreciate them because it means people are actually listening to me, which is, you know, a nice feeling. So please don't, if I'm blathering on and you don't really have a clue what I'm talking about, please, by all means, just put a question into the chat. I'm more than happy to address it. And you know, if it's a bit of a longer discussion, or if it needs a bit of a tangent, I'll either come to it a little bit later, or maybe I'll address it at the end. But please, by all means, ask them. I don't like. I'd much rather be interrupted than just talking on stuff. All right, so that's kind of where we're going. So we have our, you know, this is just to get a visualization of the various gamma. You know, if we made that bigger and bigger, you could imagine it gets narrower and narrower around this 0.25. You know, and what that essentially means is that, you know, higher values outside that range become increasingly unlikely. The probability of a lambda. Now, one thing I didn't, sorry, I talked about this a lot more last week, and I didn't mention it today, is one of the reasons I like Bayesian reasoning is I think it's a more, how do I phrase this? It's a more honest statement of what we've learned from data. And by that I mean is, let's just to kind of take a step back for a minute here. Suppose, for example, we want to get an estimate for a customer transaction frequency, right? Well, the old way of doing it was the maximum likelihood model, which was basically, if you think of it in terms of that, the maximum likelihood model, very simply put, is basically the top of a density curve. Now, that's not quite accurate, but that's kind of a very simple and simplistic way to think about it. But you're essentially optimizing the likelihood of the observation, and you're calculating that particular point estimate that maximizes the likelihood of a particular observed set of data. Okay. Now, the problem with that is, though, is that, like, that's just one value, and quite often from the point of view of practical type points of view, values around that maximum likelihood estimate are often practically, as for all intents and purposes, are just as solid an explanation for the data as the maximum likelihood estimate. So we're essentially putting a lot of emphasis on one single point estimate, then, you know, then a lot of others that are in many ways maybe not necessarily fully plausible, but, you know, still pretty good explanations, you know, are a pretty good way of explaining the data we've observed. Now, just to give an example of it, suppose, for example, we observe a week. We take a week's window and we observe that a customer makes one transaction in that week, right? Well, the maximum likelihood estimate for lambda then is 1. But it could very easily be 2. A lambda of 2 would be also very, very likely to yield one transaction in a week. So would 0, right? Like 0 transactions, right? So if we could have a lambda of 1 and we could very likely see a 2. Now, the most likely thing to observe is 1, but that doesn't mean if we observe 2 that we say it's totally impossible for a customer to have a lambda of 1. Does that make sense? So for that reason, one of the reasons why I like the Bayesian approach so much is it doesn't just give us very simple single point estimates. It actually gives us distributions of plausible values based on what we've observed. And just to show that, so let's say, for example, we combine it. So over a period of a year, a customer transacts 13 times in a year. And this is fully consistent with the prior mean, as in 52 weeks in the year, and 52 divided by 4 is 13. So we've got a very consistent value, right? So basically what we end up with is, if you look at this black line here, is our prior value, which is the gamma 1, 4 prior. But now we have this posterior distribution of it, which is the red line, right? But if you look here, there's actually quite a spread of plausible values for lambda. It's not just 0.25, even though 0.25 is our maximum likelihood estimate, right? In traditional parlance, right? But if you look at it here, say roughly here is 0.3. 0.3 isn't that implausible either. And another way to think about it is, if let's say just to take it a step back, I'm going to assume that everyone understands how a normal distribution works. If we have a normal distribution, right, even if you have a mean of 0 and a standard deviation of 1, right, if we get a realization of, say, 0.5, right, that's entirely consistent with a normal distribution of 0 and a standard deviation of 1, right? So what I like about the Bayesian approach is it gives us these ranges of outcomes, which are very, very useful for both decision making and actually performing inference on things, because we're not tied down to a single value. It's also really useful for simulation, because what I have a tendency to do is when I get model outputs, I try to use simulation to essentially validate my models. And getting a distribution of values for simulation reasons is very, very useful, because it also helps you kind of fully capture the uncertainty that's inherent in your process. So that's kind of partly why I like the Bayesian approach so much, because it's very consistent. It gives you kind of this very consistent logical framework for essentially articulating what it is we have learned from the data, given what we already knew. So let's look at, so that now, as I said, you can tell there, if you follow that black line there, that's quite a wide prior. I mean, you can see there's actually, even lambda values above 1 are actually quite probable, reasonably probable with this gamma prior. And obviously it tightened considerably given our observations of 13 and 52. But let's say we had a much tighter prior. So let's say we went with a 50-20, which is, not, a bit still consistent with 0.25, even though there's, not quite as big a spread of values. And we can see what's happened is as we've taken more data, we're getting tighter around the 0.25 value. And it's actually becoming a bit more symmetric, because I think what happens with the gamma is as the gamma comes a lot more symmetric around the mean value as the precision gets tighter. And part of that is because, the constraints of 0 is a lot less constraining on the density. But here's what we're going to do here. Like I said, based on, it might be more useful to compare the two posteriors directly. So we have 13 40, God, I have loads of misprints in this. So these are the two posterior distributions. One is based on the gamma 1,4 and the other is based on the gamma 520. But based on that, we can see that we still get, we don't have a massive disagreement between our two approaches. our posterior distributions are broadly the same. And this goes to the point of one of the reasons why Bayesian statistics was always considered quite controversial was because of these prior distributions. The fear was that you weren't just letting the data speak for itself. You were essentially influencing the answer with these priors. Now, what actually happens is in practice is that as data becomes stronger, as the evidence of the data becomes stronger, it's actually the likelihood model that you've chosen becomes much more important to the posterior distribution than the prior does. And this is a good example of it. We've got a bunch of different priors here, but you can see that, even though we have two different priors with, varying strengths, the actual, the data is a much stronger evidence than any of our priors. So therefore, the evidence is kind of dominating the posterior rather than any prior knowledge. However, that's not always the case. And it's one of the strengths of Bayesian reasoning is if you don't have a lot of data, you can still do a lot of interesting stuff. You just need stronger priors to actually get meaningful answers out of it. So that's something we're going to start using that in a workshop or two's time, when essentially we don't have a lot of evidence. Essentially, certain aspects of our data is sparse, so therefore we need to use this prior information to help codify and get like logically consistent answers, and that's perfectly fine. I mean, basically the old saw is that if you're data poor, you need to be knowledge rich to get an answer. So, but as you get more and more data, your input, your knowledge can get smaller and still produce realistic outputs. Okay. So we may not have realized it yet, but this has been actually our first like Bayesian statistics exercise. We've taken a prior, which are like kind of these, you think of these as your priors. We've made some observations 13 times in 52 weeks. And then we've updated our prior distribution to a posterior, and we now have a posterior distribution for the customer lambda. So we've now actually performed Bayesian inference on a customer. And essentially what we're going to do is that, but a lot more, right? And that's essentially what we will be doing. Now, the obvious question though is, what happens if there is an inconsistency amongst our prior and our data? So for example, let's say we have a mean value of 0.5 with the same data, right? So we have a gamma 1, 2, which is this prior here. And then we have, we basically get the same answer. But let's say, for example, we have a tighter prior, which is basically this black one here. So we have a tighter prior around 0.5, but still, because the data is still stronger, you can just think of it in terms of, 13 and 52 beats 5 and 10. It's a bigger number. So therefore, it's going to dominate the posterior. But as those numbers get closer and closer together, what will happen is you will end up with, like, if you can think of it as the distribution due to the data and the distribution due to the prior, they're going to average out, and the estimate is going to kind of end up in the middle, somewhere between the two. So if you can think of it as, like, let's say it's a 50-50 strength, then the average is going to be, 0.375, because it's halfway between 0.25 and 0.5. Okay. And, similarly, if we get stronger and stronger priors, I have all these in there. If we have a very weak prior, basically nothing happens. It's basically entirely data driven. So I've done a few different explanations there. By the way, I meant to say I've folded the code away. I do all this work in R. Most of this is very, very doable in Python using stats models and stuff like that. As far as I'm aware, you can probably pretty much lift a lot of this code and redo it in Python if any of you want to. I just tend to do most of my work these days in R. So that's kind of why I do. But I've tried to keep the code reasonably high level from a coding point of view, so that it will be relatively straightforward to transfer it into Python for any of you who are interested. All right, so that we've kind of started our Bayesian inference. That's kind of what it is. Now, as I said, we've made life very easy for ourselves here because we're just using conjugate priors. Now, in real world examples, conjugacy doesn't really work. because quite often you've got it like it doesn't fit the data, or you've got other things going on, and it breaks that nice kind of integral trick. So in the real world, we actually have to figure out ways to do this integral, and basically how do we do that? So that's where Stan comes in. So before I go there, like I said, does anyone have? I'm conscious that I'm constantly repeating myself. I don't really care. Does anyone have any questions about anything I've talked about already? Like, is there any of this stuff that you need me to go over again in terms of how you combine priors and data and all that kind of stuff? By all means, please put it in the chat. But okay, so we are now going to look at, so we've done it for one particular case, but what we want to do is we want to do it for all our customers, and we want to do it for all our customers simultaneously, right? Now, one way to do it would be to just essentially repeat this process over and over again. So we could essentially take every individual customer, give them a fixed prior, and then put it in, and that would work, right? And do that, and that would work. However, that method quickly falls short, because once you start adding any kind of wrinkles to your model, or you need to start adding anything extra, it very quickly falls over, and you need to do like proper integrals on it. Now, the way we're going to do that is Stan. So Stan is named after the Polish physicist Stanislaw Ulam. He was one of the guys who worked on the Manhattan Project, and he developed, essentially, he was one of the guys who first helped work on the Metropolis Hastings algorithm, which was the first Markov chain Monte Carlo method. So it's essentially a way of estimating high dimensional integrals. They needed to do it to basically model the quantum mechanics involved in nuclear fission, and I think nuclear fusion, but I think it was mainly nuclear fission at the time. And they came up with Metropolis Hastings for that. And it was one of those that had been around for ages, but didn't really get recognized for statistical computing until about 30 years ago. And people started writing like custom samplers and stuff. But essentially what Metropolis Hastings does is it's a way of estimating a higher dimensional posterior integral, or actually any probability distribution, but it's particularly useful for Bayesian statistics, because they tend to have these weird complex integrals that you can't really calculate. Now, I'm not going to go into the underlying technology behind how any of this works. I'm just going to give a very, very brief understanding of what happens. But for long details, if people want to know more, basically like Google Hamiltonian Monte Carlo. I'll actually put it into the chat for people who want it, and I should probably mention it. I'll go HMC, Hamiltonian Monte Carlo. Hamiltonian Monte Carlo is kind of at the cutting edge of where statistical computing is today for working on these kinds of problems. Essentially what it does is it uses ideas from physics. So the way to think of how Hamiltonian Monte Carlo works is we can think of our probability distribution that we want to explore as being a surface in phase space. And essentially every parameter in the model becomes a distribution in our probability space. So we can think of it as essentially, if we think of it this way, right? We have 1,000 customers, right? We have a 1,000-dimensional problem because every lambda is its own dimension in this phase space. So we're essentially exploring a 1,000-dimensional phase space, right? And as you can imagine, trying to do that directly is completely impossible. In fact, I think after about trying to do it kind of analytically or even numerically, after I think 3 or 4 dimensions, it basically falls over. Certainly by 10, you just end up in calculating zeros all the time. So instead, what we try to do is produce values from the posterior distribution that are how do I phrase this? You take a point from your sample, and as an ensemble of samples of iterations from that sample, we then get a representative sample from the probability distribution. Now the question is, how do we do that? So then so let's say we have 2,000 sample iterations from our sample. Well, we now have 2,000 sets of values that are explained by the data that we observed. The way it works is it's some very, very cool technology. Essentially, it's called Hamiltonian Monte Carlo because it uses physics ideas. So essentially what they do is you assume that the particle, you think of it as a particle that's on a hill. And that hill is a multidimensional hill, which is kind of like a potential, right? And it's moving around the hill, right? So if you think of it in like three-dimensional space, if we think of it as a two-dimensional distribution we're exploring, you know, the particle is more likely is kind of heading to going up the hill and down the hill and stuff like that. So essentially what we do is and you need a random element. That's where the kind of the simulation comes from, because like I said, it's Markov chain Monte Carlo. The Monte Carlo aspect is you create like a random number, and then you use that random number to generate values in the posterior distribution. So from a physics point of view, what it is we randomly generate an n-dimensional momentum, and then we use the probability distribution we're trying to sample from is the potential of that distribution. So it dictates where it goes. And then we use the momentum. It basically tracks the trajectory of the parameter of the particle through phase space. Using the momentum and the position. And then the position of the particle are basically the samples from our distribution. And it uses a whole bunch of very, very fancy and clever kind of numerical computation to calculate all of this, using things like automatic differentiation and stuff to calculate the vectors, because you don't just need the values, you also need the gradients to be able to calculate these things properly. But it basically uses a bunch of fancy maths to create this sample, and that sample is the output of our model. How are we doing for time? 8:30, perfect. So I'm going to run until about 8:45 probably. So we've got about another 20 minutes. Cool. So like I said, there's a whole bunch of very, very interesting, like Michael Betancourt did most of the theoretical, or a lot of the theoretical underpinnings for this. If you look at the STAN team, there's a whole bunch of very good videos where they talk about a lot of the stuff like that. I could go into it here, but my understanding of it is not good enough to teach this properly because it can get quite technical. But Hamiltonian Monte Carlo gives us a few things that on the surface seem bad, but are actually very good. And what do I mean by that? Well, basically, sometimes Hamiltonian Monte Carlo fails, right? Essentially, it's called a divergent transition. And if you're doing anything to do with STAN or PyMC3, to be fair, anything to do with STAN or PyMC3, you will likely encounter these things called divergent transitions. And essentially what happens is that numerical integration of the trajectory of the particle through phase space fails. And it fails basically for a bunch of reasons. But the main reason is that the geometry of your posterior is problematic in some way. And what that effectively means is that you have a misspecified model. And the reason why that sounds really bad, so when you start using STAN, you'll probably start getting all these divergent transitions, and it becomes very popular. People complain a lot, and people get kind of disheartened. But what has happened is that these divergent transitions is actually STAN telling you that there's a problem with your model that you need to fix. And the reason why these things didn't manifest before is because you weren't trying to explore the entire phase space. You were just trying to it was an optimization problem looking for a single point value. And because of that, a lot of these problems with the posteriors that you were creating kind of got ignored, or they were manifest. Like one of the things that have a lot of people talk about are they have problems fitting what are called mixed effects models, which are hierarchical models that we're going to be talking about in this workshop, but they often can be difficult to fit. And one of the main reasons why they're difficult to fit is because they're actually a misspecified model. So there's a thing in computational statistics called the Folk theorem of statistical computing. And a Folk theorem is kind of the idea, it's like a conventional, I don't want to say conventional wisdom, but it's kind of a thing you learn through experience. And it's basically that computational problems tend to be model problems in disguise. So essentially, if you're having problems fitting your model is probably problematic in some way. And that can manifest itself in a bunch of different ways. But what it essentially means from a practical point of view is that the model you're fitting is trying to fit on data that don't match the model you're trying to fit. And as a result, you're getting these problematic areas that the Hamiltonian Monte Carlo sampler is having problems exploring. And it was problems like this that actually motivated the use of these techniques in the first place, because there's a canonical kind of hierarchical model distribution, and hierarchical models are kind of why people got into all this kind of stuff. And I'll explain why hierarchical models are cool. Probably won't get to it today. But essentially, it's called the 8 schools data. By all means, look it up online. But Andrew Gelman, who's kind of one of the leading academics in this field, I think he either forgot or just for an experiment. He was going away for a period of time, like Thanksgiving weekend or something, and he wanted to see what would happen if he left a sampler sampling for a long period of time. And what they noticed was, and this was kind of a hello world problem, and what they noticed was that when they did what's called a trace plot, which is basically like, you can think of it as like a sequence plot of the parameter outputs of a model for a single parameter, he noticed that the model was actually flatlining, which means it was getting stuck. And they realized essentially their model was problematic. This kind of basic, simple hierarchical model that everyone was using as like the really simple example of why hierarchical models are cool, they realized, oh, actually, our model is wrong, and we didn't realize it because the other samplers that we're using weren't really able to handle these problems. Whereas Hamiltonian Monte Carlo kind of could tell there was a problem and immediately gave you issues. And that's something we might get to a little bit later in the workshop. So the point I'm trying to make is Hamiltonian Monte Carlo, or HMC, is really good. There's a whole load of extensions to it now that work in practical points of view. But basically, Stan is built on top of HMC, and it means that we don't have to worry about the really important technical things that need to be done when writing a MCMC sampler. Stan just kind of does it for us. It's kind of done, and we don't really have to worry about it. Now, we'll have to worry about how we specify our models, and if we get divergent transitions or what's called the Bayesian fraction of missing information. If we have what are called mixing problems, then we still have to think about our model, but it means we don't actually have to debug MCMC code, which is basically how people used to have to do it, which was problematic and incredibly time consuming. The idea of all this is people who just want to do statistical computation and fit models can take Stan and use it to fit their models, and they can build quite sophisticated models with this because it's essentially a programming language. As long as you have the data that supports it, you can fit kind of any model you like. Now, whether or not that model will actually give you a valid sample is a different issue, but at least in principle, we can do all this. So that's kind of a long-winded introduction to saying we're going to use Stan to fit this model. And we're going to build a very, very simple one. I'm going to talk about the Stan code. Now, Stan is written in C++, and specifically, it's written in templated C++ because they need templates for all the automatic differentiation to work. And they had to write their own auto differentiation, which basically allows us to take a function and automatically calculate the gradients on that function without actually having to hand code the gradients. Because as I said, we need the gradients for these suite of algorithms to work effectively, to be able to calculate trajectories and stuff. So basically what we're looking at, the key thing I want to point out is this number down here. So this is a Poisson LPMF. It's a log probability mass function. And we're basically saying that BTYD is the count. So this is the number of observations of a customer. And so we have n observations. So we're sending n values into Stan. We have n integers with a lower value of 0. So the count data is in essentially an array of integers, right? And that's our counts. And the number of weeks observed, because different customers can have different observation weeks, was that. And from that, we have our parameters lambda. And again, we have a vector of n values of lambda. And we're basically saying that, I'll get to the target plus equals in a minute, but basically with a Poisson likelihood, which is what this is saying, we observed this amount of observations given this lambda times t and x times the weeks. So we have a transaction rate, which is lambda that we're doing the inference on, because that's our parameter here. And then lambda is a rate per week. We obviously have different weeks that things were observed on, and I will get to why that's important in a little bit. And that's basically our stand model, right? So we have some data input that Stan is expecting. So it's expecting 3 pieces of data. It's expecting a single value n, which is basically the length of our vectors. It's then suggesting, it then wants an array of integers, which are all our integer counts of the number of observations over a given time period. And then we have for each observation count, we have the observed time period, which is at the weeks. And then it's just like lambda is just lambda times the time window is our lambda, is our input lambda. And then we've observed this BTYD count given lambda. And then the target plus equal means basically update the log probability model. So essentially what happens is all these things happen in log probability space, because essentially you're dealing with, for rounding reasons, it's better to deal in log space rather than do all these multiplications and have rounding issues. So that all these things tend to be, so rather than multiplying in probability space, we add in log probability space. So that's basically what we're saying here. And then as a result, we will, like if we put 1,000, if say n is 1,000 and we have 1,000 counts and then 1,000 values for the week observations, we will end up with a posterior distribution for 1,000 lambdas. Okay, so that's our stand model. That's just a text file. Now I've, you know, this is it's just for the purposes of the this worksheet. You know, it's putting it in space, but that is just to show you if we bring it up in the code. And the nice thing about all of this is it's in, when we do it in our studio, you know, there's some nice syntax highlighting and stuff. But those 14 lines of code, including white space, is basically our stand model. And that will essentially take each individual lambda and it will create a posterior distribution for lambda. Now, we don't have a prior in here. So when you don't give a prior, first of all, you shouldn't, but for teaching reasons, I'm doing it now. It basically just assumes a uniform distribution, which is bad for reasons I will get to in future workshops. But at this point, we're basically saying lambda could be any value whatsoever. So just sample based off the likelihood, where it's essentially like a uniform prior. Now, that seems like a good thing when you first initially think about it, because it basically means you're not essentially biasing your answers with any kind of, you know, prior distribution. But when you think about it a little bit harder, you realize it's kind of nonsense, because you're actually giving, that is not informationless. What you're basically saying is that without any observation of data, a lambda value of like 10 million is as equally likely as a lambda value of 1 or 0.5 or 0.1. And we kind of know intuitively that that's kind of nonsense. So that's why uniform priors are very, very bad practice in these, because you're essentially creating areas of positive probability mass out in ridiculous values, because essentially it either goes, if it's an unbounded probability distribution, it goes from minus infinity. Every parameter essentially has a prior going from minus infinity to plus infinity, and they all have an equal weight. Or if it's bounded, it goes from the lower bound to the upper bound, which could be, say, in this case, it's from 0 to plus infinity. But you can also have like bounded distributions where it goes from A to B. But you're basically saying every value in that range of values is equally likely. And when we've got like infinite ranges, then you're essentially saying those ridiculously large values are as equally important at the start as smaller values. And that can actually cause problems. You can actually have sampler errors as a result, because essentially the data, the prior is saying to look out over here, and the data is saying, no, focus just in this area here. So that's why using uniform priors is generally discouraged. You're better off having some kind of weak, that, like, if you think of it as a regularization of the model, you're basically saying that, you know, not all values are equally likely. I kind of know that the values are between, you know, 0 and 10. So I create a prior that, you know, has a probability mass somewhere in the middle, and, you know, the vast majority of values are going to lie between 0 and 10. And that actually makes your sampler behave better, because then your data is consistent with the prior model that you've got, and you just end up with a better geometric shape that you're trying to explore, and as a result you get better stand outputs. Okay, so basically we can fit our model. I'm using command stan R to fit the model. I'll just quickly, I don't really want to go into the code too much, but just to show you, we need to compile our model, which takes this is our like stan code. It converts it into templated C++. And essentially the output of a stan compilation is a binary file that takes data in and spits out a posterior distribution. And it's a little binary file that does all that calculations for us. And then command stan R is, command stan is like a command line utility that does all of this for us. There is also a library called rstan, and that integrates much more tighter with R. But I have found that generally command stan R is better than rstan, although there are a few functions in rstan that are better. Also, rstan has problems with cran and just the memory. It's basically, it does everything inside of the R function, whereas command stan R like forks out a separate process, builds it, runs the sampler in that separate process, and then writes things to disk. And then command stan R has routines that allow you to read from that. And I just found, especially when working with RStudio, command stan R is better. But if you want to do things in rstan, basically, especially for these kind of things, it will give you exactly the same results. So we're going to build our command stan model, and this is just saying, you know, where to include from and, you know, where to output our data. And then we have a routine, which is this sample. So it outputs this stan model, and then stan model has a routine called sample, where we put in the data, the chains and the iterations and stuff I'll get to in a sec, and the seed. But basically this produces our stan fit. So we have stan data. And again, I won't get into, I'll talk about this in a lot more detail next time, which will probably be in March. But essentially what we're going to do is we're kind of setting the data up into a format that Stan can read very easily. And this compose data does that and this is all coming from a package in R called TidyBase, which kind of does a lot of this plumbing for you. And then we're just fitting the model, and then we get an output. Now, to talk about this, let me just get into these details a little bit. So the 4 chains is essentially the way Stan works, like I said, is you sample using multiple chains. And the reason for that is, there's a couple of different reasons for it. But first of all, a chain is essentially what we do is, rather than just run one long iteration of that particle through phase space, we instead have multiple particles that we project through phase space, and then we basically take the trajectories of all those particles. The count of particles are called the chain, and this is like, if you remember, I said it was Markov chain Monte Carlo. Now, the basic idea is, the reason why it's called Markov chain Monte Carlo is we're actually creating a Markov chain. So essentially what we do is we sample a point in space, and then once we have that point in space that we're happy with, that's part of the sample, we then do what's called a transition to the new particle. And then we have what's called an accept, and we basically say, okay, let's check. We know that this point is good. How about this new point, which is like some perturbation from this point here? Is that good? And then if it is, we accept the new point, and we have some way of accepting new points. Or maybe it isn't, and we reject, and we create a new proposal. Okay? And that was the original. That's like, if you look up Metropolis Hastings, there's a very, very simple way to do all that. Now, essentially, Hamiltonian Monte Carlo is a much more complex, a complex version of that. And that succession of transitions with all those points in parameter space, they form what's called a Markov chain. And to explore the posterior space as much as we possibly can, we want to use multiple Markov chains. And the original reason for it was because basically we wanted to check mixing. So essentially, the point I mentioned there was how do we know that? How do we start? Like, where do we start? Well, we start at a random point in space, or we like at 0 or whatever. And that becomes our first point. And then we go to another point and another point and another point. And the way it used to have to work was basically we would do that a whole load of times. And eventually, because of the way Metropolis Hastings or because of the way Markov chains work, after a while, once you iterate this process over and over again, you end up in the target probability distribution that we want to sample from. So as a result, we would run multiple chains so that we can compare chains together. And if we do what's called a trace plot, so we plot a single parameter like in sequence from the Markov chains, if you did a plot of all those chains at the same time, you would find that they would start out at the different places where they chain, and then they eventually kind of converge into like around a value that's the posterior sample. But the question is, we never necessarily know when our Markov chain has converged. So that was why we run multiple chains to try and get a sense of how that worked. Now, that has become less necessary with these more modern techniques, because like I mentioned before, we now have a gradient. So what happens is the gradient points us in the direction of where in probability space we want to explore. So nowadays, we don't necessarily need multiple chains as much from that point of view. But what we do need to do is that whole Hamiltonian Monte Carlo thing that has all this physical adaptation, while it works in terms of getting into the sample space, we also, because it's very, very high dimensional, we care a lot about sampling efficiency. So we want to make sure basically that our computations aren't wasted and that we use as much computation as possible to actually create a good sample. And because we're dealing with very, very high dimensional values, and in many cases, you know, data that are used, this stuff can take quite a while to run. So now what they do is, rather than trying to make sure that your Markov chains have converged, because basically after a few iterations, you tend to be in the area of high probability mass, what we essentially want to look at is we need to do what's called an adaptation step. So essentially, we do some sampling over the probability space, and we're using those initial iterations to figure out what the optimal parameters are for the Hamiltonian Monte Carlo to sample efficiently. So you now have what's called a warm-up. So the warm-up, and generally your warm-up iterations is half of your sampling iterations. So in this case, we have 500 warm-up, 500 sampling. And the idea of that is we're essentially trying to set, basically, if we didn't have this, we would have to tune Hamiltonian Monte Carlo ourselves. And that can get quite fiddly and messy and kind of defeats the purpose of Stan in the first place, because you need to know the intricacies of your sampler, which they were trying to avoid. So instead, what we want to do, we want to run multiple chains, exploring as much of the space as we possibly can, so that the sampler gets as much information about the geometry as it can get, which means it can set the parameters for the sampler as efficiently as possible, and then we run our sample. And then also, from the point of view of checking the sample quality, we can then look at our chains and make sure that, you know, essentially each chain is giving roughly the same value for each parameter over time. So essentially what you want are flat lines. Now, I actually don't have any trace plots in this. I'm just realizing that I should probably include them, because that will help visualize this a bit more often. Now, I realize as I'm saying all this stuff is complex. Like, this stuff is not easy and it's not straightforward to do. It's not just a question of, you know, taking a library and fitting up data to it and then coming up with answers. This stuff is a bit more complicated, and there is much more of a learning curve to that. Now, unfortunately, there's no real way around that. But the flip side is kind of, once you learn that, and once you actually realize the power of what these things can do and are willing to go on that journey, it suddenly opens up a whole load of modeling that wouldn't have been available to you before. You can now like tackle problems that were essentially you couldn't deal with before, because your standard algorithms don't kind of deal with the specific situation. So I'm going to talk about this more next week, and I'm hopefully going to have a bit more kind of visualizations to help explain like the traces and all those kind of things. But basically, just to look at the outputs, we essentially get outputs here. This is what our posterior output looks like. It's a big table of data, which I appreciate is horrible. But we have these lambdas. So this is lambda 1. This is customer 1, 2, 3, 4. We have 1,000 samples. We have this log probability. We don't really need to worry about that. But for 1,000 customers, we now have, how many did we do? I think we have 1,000 parameters. We have 1,000 iterations in our sample and 1,000 lambdas. So every customer has a lambda value now, and we have a sample from the probability distribution for that lambda. Each customer has their own posterior distribution for lambda, basically. And that posterior distribution has 1,000 samples in it. So we can now get a pretty good estimate of our uncertainty or our statistical inference in the lambda, okay? And next week I'm going to start, or next month, we'll probably have another workshop, probably around this time in March, because I don't think we're going to have a talk in March. It's not looking likely. It's probably going to be April or May. When we come back next week, I'm going to talk about this in a bit more detail in terms of like the last things I've been talking about in the last, say, 10 or 15 minutes. We're going to talk a bit more about sampling and trace plots and all that kind of stuff. And then we're going to start looking at these posterior distributions and seeing how we can compare it. Okay, actually, I'll show you. No, that's a posterior plot. So, well, actually, I can show you here. Has that finished? It has. So let's build our very first. Just before you go, let's have a quick look at it. So we have the model fit. So we have a freak model, flat stand fit, and tidy bays, tidy draws. Let me just gather. Actually, I have it here. My apologies. So we have, if we look at the value here, we have a customer ID and we have the draws. So let's just take that very first customer ID. And I've done some jiggery pokery that converts the indexes in Stan back to the categorical variables in R. So, and that's using basically just some code there. It's all in the code if you want to look at it. No big deal. But it's definitely a quality of life thing that we can look at. And let's do a histogram of geom histogram. I think it's, what is it? Is it post lambda? Yeah. So this is our posterior distribution for that first customer. So we have a histogram of the samples of lambda. So we can see, you know, it's kind of around, it looks like this customer has a transaction frequency of about 0.02. So like one transaction maybe every 50 weeks, maybe a bit more, maybe every 0.03, something like that. And we have one of these for every single customer. So now we can actually get a good estimate of the certainty. Like not only do we have an estimate for the lambda values, we also know how much confidence we have in those estimates as well, which is dictated by how wide the posterior distribution is around that central lambda. So, and that gives us quite a lot of power, because what we might find is, we might find that we have customers who have a relatively high transactional frequency, but a very, very large estimate of the uncertainty, right? What are the, I'm sorry, I'm not sure I understand, Yash. What are the, oh no, sorry, that's the, that particular value there, is that what you mean? Those are the pre-programmed values. So if I mentioned it before, I'll talk about this more next time, but essentially I generated this data synthetically, so I know what the true answer is. Now in the real life, we wouldn't know that value, but basically I can then check how good our models, how good is this approach in general, how well does it work? So if the customer lambda was the value of lambda that particular customer was given when we generated the data. So I can compare our posterior distribution based on the transaction count that was observed against what the actual customer lambda was. Okay, so I'm going to leave it there because I appreciate it's a lot to take in. Does anyone have any questions just before we go? And I'm happy to stay on for a few minutes if anyone has any questions. But if anyone has any questions right now, please ask them. You've got, you know, a window of a minute or two, and then after that, I'm going to stop the recording. If anyone has any, for achieving this using Python, what's the difference between PyStan and PyMC3? From an underlying technology point of view, almost nothing. As far as I'm aware, the two teams collaborate quite a lot. PyMC3 is written in pure Python. Like it's a library, you import it, it all works. It's written in Python, it's slightly different. Whereas PyStan actually uses Stan code and then writes its sampler. And then PyStan kind of like in R, it's kind of written in Stan and it does all its sampling in Stan. Whereas PyMC3 does its sampling in Python. Although I think PyMC3, it used to be built on top of Theano for its auto differentiation. I think it's built on top of something. Oh no, they preserved Theano. If we're computing separate lambdas for each customer, have we not got 1,001 customer? Yes, we do right now. But from a sampling point of view, it was one model with 1,000 parameters in it. But in this case, we could have broken it down into completely separate samplers, yes. But what happens later on is we can start using things like hierarchical models, which uses partial pooling. So for the values there where we don't have a lot of data, we can actually learn something from the customers who do have a lot of data. And that's something I'm going to talk about a little bit more in like the next workshop. But thanks for that question. Does that make sense? Sorry, in that question about the separate models? Yeah, right now, yes, you're absolutely correct. We could have faced 1,000 separate models, and that would have been, and to be fair, that would have been much, much quicker. However, what this allows us to do is to do much cleverer and fancier things that we wouldn't be able to do as separate models from one another, because you need the whole thing to be able to do the better models, if that makes sense. Because customer behaviors inform one another, because overall, it's called, like, essentially with hierarchical models, it's kind of like what regularization does in more machine learning things. It kind of means that we can throw out kind of silly large values and we can learn from how the group behaves as a whole. Sorry, just to go back to the answer. So in Python, so the Python and Stan have an interesting, there wasn't much, the Stan guys were always very pro Python, but not a lot of them wrote it because their background was mainly stats. So you had this weird dichotomy. You had a bunch of like hardcore C++ kind of software development engineering guys, including the main guy, Michael Betancourt, who did a lot of the underlying statistical theory. That they wrote a lot of stuff in C++. And then you had kind of the less software development guys who came from statistics who did a lot of R. And there was only one or two guys that were kind of big Python heads involved. That has changed a lot in the last 5 years. There's a couple of pretty big kind of probabilistic guys. I'm not sure why they never got into PyMC3, but for whatever reasons, they're in PyStan now. It is very much a question of picking your poison. I mean, if I was to use Python, I would use PyStan because it would mean I wouldn't need to learn something new. And as far as I can tell, in terms of what they do, I think the PyMC3 guys have gone down a bit more down the machine learning route. So they're going down things like torch and approximate Bayesian inference and stuff like that, which has become a bit more popular in machine learning circles. I don't really like a lot of that because you lose a lot of the diagnostics that you get from Hamiltonian Monte Carlo. But it's very much a kind of a pick. But the flip side of it is that you can deal with much larger data sets. But for the kind of work I do, I like to know when my model is wrong. And the problem with using some of those bigger data sets is that you don't know if your model is wrong because you've lost all those kind of diagnostics that you get from running your sampler on HMC. The downside is, though, that HMC takes a lot longer or can become infeasible with very large data sets. Okay. Any other questions? Not a problem, Yash. I think you have my email address, Yash. If you have any more questions, or if I can give you any more help with that, just pop me a mail, or like organize. Just give me a shout. We'll organize a call. I'm happy to help out. I know a couple of people who used PyMC3 a lot, and they're big. And I know most of the Python community who are doing Bayesian inference use PyMC3, because, like I said, when this stuff became kind of got popular, and Stan was, I think, 2012 or 2013, because there wasn't many people on the Python committee. It basically, and PyMC3 was around. A lot more people do that. However, having said that, there isn't any really, rivalry. The main guy in PyMC3 is a guy called Chris Fonnesbeck, who's really sound. And I think the two of them kind of, essentially help each other out quite a lot. And like I said, there's been kind of a more of a move towards the more machine learning frameworks on PyMC3, because it's got that more kind of generic top end stuff, whereas the Stan guys have very deliberately avoided doing that because they don't want to go down the route where you don't have good diagnostics for your posterior samples. Okay, well, thank you very much. Like I said, I'm going to stop recording now. Let me just do that first, actually.